Good afternoon, everyone. So here I begin my session, that is the live interaction session for the week 2 for the mathematical methods in physics. So this session will be chaired by me. So my name is Biju Shaha and I am a Prime Minister Research Fellow at ISAT Tirupati, and I will be hosting this interaction session every Sunday at 4 to 6 p.m. So this is my week 2 of the interaction session. So for the people who already are aware about the rules I follow in the interaction session, may know that I I intend to discuss few problems which are related to the topics that were being discussed in the week 2 of the mathematical methods in physics, that is the previous week. So in the process I will present you with a problem, and before heading out to solve the problem I will review the concepts that are required to solve the problem. So since this is an interaction session, I would like for the people who are yet to join and who are in the process of joining to to also pose their questions to me and also approach how to solve the problem as I present the problem to you. So this is the rank. This is the concept which is known as the rank of the matrix. So this is something which I already discussed in the previous session. So right now I am going to give a brief recap of the same concept because it is required for this session. It is important for this session itself. So yeah, I hope I am clearly audible, right? Okay, so I just started. So the concept that I'm going to present at the very beginning is the rank of a matrix. So the rank of a matrix is something that I discussed in the previous week. So the rank of a matrix was as follows. So first of all, we have to if we are given a matrix, we have to reduce it into a form which is known as the row reduced form. So the row reduced form of a matrix, takes the form as follows. So given a matrix, let's say we are given a 3 cross 3 matrix. Reducing it to a row reduced form would mean that the leading entry of every row, is 1, and the all other entries in the columns containing the leading row is 0. This is something we achieve by performing several row operations. That were being discussed in the previous class. So again I'm going to give a brief review of it. So in order to bring down the matrix into a row reduced form, I have to perform the few elementary row operations. So the row operations are either I can interchange the two rows, let's say in a way, in the method of moving from this original matrix to a row reduced matrix. I perform several elementary row operations. That one row operation which is valid is interchanging two rows. That is one such row operations that are possible. The other row operations are we multiply a row by a non-zero constant. So we are also allowed to multiply a row by something, by non-zero constant. So that is also allowed. And the third thing that is allowed in the elementary row operation is adding a multiple of one row to the other. So let's say we have a row called R2. So to this R2 we can add a multiple of the other row. So this is something which we have discussed last class. So this is how we bring down a matrix to a row reduced form. So this is my original matrix, and after performing the several elementary row operations, that is this particular three transformation on the rows, I can reduce a matrix to a row reduced form, which looks like this. And after having reduced it to a row reduced form, what exactly I have to do? I have to count the number of rows which can contain at least one non-zero element. So this particular matrix, in the row reduced form, it contains three such rows which contains at least one non-zero element. So that says the rank of this matrix is equal to 3. So provided this brief recap of the rank of the matrix, let us move towards solving the first problem. So in this session I will mainly discuss 12 such problems that will help you solve the problems that are given to you in the assignment. So that those are based on the topics which were discussed in the previous week. So first of all, the problem 1 goes as follows. We have a system of equation that is represented in the following matrix form. So we know a given set of equations, simultaneous linear equation, can be written in the form of a matrix equation. So this is the matrix form of the simultaneous linear equation. So we have to find whether the above system of equation, is it consistent or is it inconsistent. So let us go about solving this problem. Yeah. So we have the following set of equation represented in the matrix form. So let me rewrite the matrix equation. Yeah. So this is something which is known as the augmented matrix. So a part of it is known as the matrix of coefficient. So this block I can say is the matrix of coefficient, which contains the coefficients attached to the variables on a, like, if we have system of equation which is given of the form of LHS equal to RHS kind of form, then this particular matrix of coefficient is obtained from the LHS part, and the constants which appear on the right hand side, when we augment it to the matrix of coefficient, so I have just augmented the matrix of the constants on the right hand side to the matrix of coefficient. So that is the total matrix is now the augmented matrix. So right now we have 5 such rows and 5 such columns. So that in turn means that in my system of equation there are 5 unknown variables. There are 5 unknown variables, provided we have 5 unknown 5 equations given. So now we have to find out whether the given system of equation represented in the matrix form is inconsistent or consistent. So this is our task to carry out in this exercise. So the way to go about this is to reduce this augmented matrix into a row reduced form. So to reduce it into the row reduced form, there are several row operations. So that has been discussed in the last class. So I would like to so the leading row should contain 1. So obviously the first row, the first element itself is 1. Now my job is to make all other elements present in that column to be equal to 0. So that can be done by performing row operations. So these are the following row operations that you can perform. So if you just So this is the first row operation that you can perform, like just add the second row to the modify the second row such that the new second row is the sum of the second row and the first row. So R2 goes to R2 plus R1. Similarly, we can also, with the motivation of making this and this element to be 0, so what row operations we can perform? We can perform the following row operations. Yeah, so these are the row operations we can perform, and with these row operations being performed on that matrix, the matrix changes to something like this. So we have made all the elements in the first column to be 0 except the leading entry. So, and obviously since we are performing it over the entire matrix, so other columns are also going to get affected, that is for sure. So this is how the entire matrix now changes. Yeah. So right now let us move to the second row. So in the second row, so right now my focus is the second row itself. So in the second row now the leading entry is present in this third column. So now my job is to reduce all these other reduce all these other elements to be equal to 0. So similarly I can perform with that motivation, I perform the following row operations. Yeah, so R1 minus R2, that makes this one 0. So R3 goes to R3 minus 2R2, so that makes this 0. So likewise, all other elements in the same column goes to 0. So after performing this row operation, my matrix reduces to this form. Yeah. So now my focus should be on, since I have already operated on the second row, let's go to the third, like the third row. So this is my third row. So right now again I perform some row operations, so I'm not writing it again, so you can solve it out by yourself and can figure out that some row operations if you perform, you can reduce the augmented matrix into the form which is being given as follows. Yeah, so this is the right now it is in the row reduced form because it obeys all the criteria that is to be satisfied, that has to be satisfied. So you see the leading rows are always 1, leading element in the rows are always 1. So this is my leading elements, they're always 1, and all other entries in the column containing the leading rows are 0. So they are all 0. So right now I have reduced the matrix to a row reduced form. So right now if you just write this particular augmented matrix form, so this is an augmented matrix reduced to a row reduced form. Yeah. So right now when I split it into equations, then from this third, from the fourth and the fifth row, I obtain a row, I obtain an equation which has been given as follows. Like every elements are 0, and since there are 5 unknowns, equal to minus 4. Similarly, I obtain something from this fifth row also, 0 dot x1 plus 0 dot x2. Yeah. So this is something which is very impractical, because whatever value you multiply to 0, it should turn out to be 0, but there are non-zero elements on the right hand side. So that makes the system inconsistent. So this system is turns out to be inconsistent because no values of x I from I goes 1 to 5 will satisfy these two equations in any scenario. It won't satisfy. So that is why this set of system is inconsistent. So this same conclusion can be arrived by if you calculate the rank of the reduced matrix. So when you see, so rank of the augmented matrix, so let's call A as the augmented matrix. So the rank of this augmented matrix is the number of rows which contains at least one non-zero element. So when you look at the entire matrix, obviously there are 5 rows which contains at least one non-zero element. So that is why rank of augmented matrix is 5. On the other hand, rank of the coefficient matrix. So coefficient matrix is up till this part. So in this, the number of rows containing at least one non-zero element, it has been given by 3, because the last two rows contain no non-zero element. So here you come to one inference, that if your rank of the augmented matrix is not equal to the rank of the coefficient matrix, that says that the system of equation is inconsistent. So this is a very important conclusion from this. So without having to solve the equation, or without having to solve like 5 set of simultaneous linear equation, if you just calculate the rank of the augmented matrix and the rank of the coefficient matrix and find out them to be unequal with each other, then you can easily conclude that the system is inconsistent. So with this, let me present to you another set of equations with a slightly different right hand side. So this is what our original matrix was. So yeah, so this is what our original matrix was. So let me just change this matrix, change this value on the right hand side, that is change the constant. So whatever was appearing on the right hand side, I just changed there were 5 such equations, so I just changed the last two values from earlier it was just 1 and 1, so right now it is 3 and 4. So, and similarly I can perform row operations on this, just like how I perform the row operations here. By performing similar row operation, I can arrive at a row reduced form of this matrix, which looks like this. Yeah, so okay, so it is almost similar to the row reduced form of the earlier matrix. So earlier matrix was like this, so I can just copy paste this part. The change occurs in the last two rows. Yeah. So this is how the right now the row reduced form looks like. Yeah. So this is how the row reduced form for this particular system of equation looks like. So what you get to see here is the second last and the last row has now taken a form which is consistent. That is like even both the left hand side and the right hand side equal to 0. So that like kinds of releases us from this inconsistency problem. So let us go further and check what happens from the first three rows. Does that give rise to inconsistency, or does it make the system consistent? So when I actually write it, so this is the form that I get when I express the first row. Yeah. And the other rows looks as sorry, this is x5. Yeah. So this is how the now my resultant system of equation looks like. So what there are now cases like you have to look into how many number of constants, how many number of variables there are, and how many system of equations you have. So in hand you have 3 equations, but you have 5 unknown variables. So that if you solve 3 equations, you will get 3 independent solutions. So there is like number of equations is greater than the number of unknown variables. So that says that there are presence of leading variables and free variables. Free variables means you can change the variables according to your wish and get a solution for the leading variable. So here actually the leading variables and free variables are as follows. So when you actually look at this augmented form of the matrix, for the first row the leading entry is present in the first column. So that would multiply with the x1 if I were to express it in this form. So when I expressed it in this form, the one coefficient multiplied with x1. So x1 is the leading variable. Similarly, from the second row, when you see the third column contains the leading element. So then x3 is another leading variable. Similarly, from the third row, x5 is the leading variable. So right now we have to be leading variable, and the remaining others are the free variables. So x2 and x4 are the free variables. So given any value of like the free variable, whatever you can obtain many such value of leading variable. So you're free to choose any value of the free variable. So let me pick x2 equal to 0 and also x4 equal to 0, the simplest scenario. So with this free variable, what you obtain when you solve this, so x5 is equal to 3, and when you put x2 equal to and x4 0, so this I'm going down to 0, and x5 is already known to be 3, so x3 turns out to be minus 6. And similarly, when I put all the values, like I already know x2, I have already chosen my x2 and x4 to be 0, and from this x3 and x5 if I put, so I end up getting x1 equal to 4. Yeah. So the solution to this is x1, x2, x3, x4, x5. So my leading variables has achieved the value called 4, 3 and 4 minus 6, and x5 is equal to 3. So these are the value of the leading variables given the value of the free variables with 0 and 4. So right now 0 and 0. So right now you can pick any two values of x2 and x4. You can even choose x2 as, let's say, x2 equal to 1 and x4 equal to 5. Then you will obtain a different set of values. So you will obtain a different set of values. So likewise you can keep on choosing the free variables to be any value and get infinite number of such solution. So that brings us to the conclusion that this set of equations that were represented by this matrix form is actually consistent. They are definitely, they are consistent because we could solve them, but there is no unique solution. So it's non-unique and it has infinite solution. So now when you look into this particular approach through the point of view of rank of the matrix, what you get to see is that, so right now here the rank of the augmented matrix for this particular equation, the rank of the augmented matrix is equal to 3. So because there are like 3 non-zero rows, but and also the rank of the coefficient matrix is also 3. But the number of variables is 5. So when you compare them, and we can write it in a form like when rank of the augmented matrix is equal to rank of the matrix coefficient of the matrix, but it is less than the number of free variables. So if m is the number of free variable in this criteria, if this criteria is satisfied by any system of equation, then we conclude that the system is consistent and has infinite solution. So this is one such conclusion. So now, right now, another case you might have already in your head, that what happens when like rank of the augmented matrix becomes equal to the rank of the coefficient matrix, and they are also equal to the number of variables. So in such case, we have the system to be consistent and the equation, the solution is unique. Yeah. So let us take one example in this regard. So yeah. So let's take a system of equation which is already reduced to a row reduced form. So without having to go through the process of elementary row transformation, which you are already familiar with. So I'm directly writing the row reduced form of a system of equation. Yeah, so it is in a row reduced form because it obeys all the properties of it. So from here what you see is the rank of the, so it's a 3 cross 3. Yeah, it's a 3 cross 3 matrix. So there are 3 unknown variables. That is for sure. 3 unknown variables are present, and also rank of the augmented matrix is equal to the rank of the matrix of coefficient, which is equal to 3. So this system of equation is consistent and also it has unique solution. So how to obtain the solution? Next thing is how to obtain the solution. You go through a backward substitution. So the backward substitution means that start with the very last row because it has just one non-zero entry. So that thing would be just x3 equal to 2. So now you have achieved the value of x3 and go in a reverse direction. Now go to the second row. x2 minus x3 is equal to 3. So x3 you already obtained to be 2. So that gives x2 equal to 5. Now put x3 equal to 2 and x2 equal to 5, x equal to 2 and x2 equal to 5 in equation 1. So that gives me x1 equal to minus 2 of x2, which is 5, plus 2 of x3, which is 2, equal to minus 2. So that gives me x1 equal to 4. So this is how like now right now there is no case of free variable or leading variable. So it's completely an unique solution. We're given by 4, x2 was 5 and x3 was 2. So this is the solution for this equation. So these are the 3 important I can say the important results from this, which will be very helpful in today's like exercises and also helpful in solve the assignment problems. So yeah, so these 3 results. Okay, now let me move to the second class of problem. Yeah. So this was our problem 1, and this is what was problem 2, that I changed the values of the right hand side, and the equation turned out to be consistent but infinite solution. Now again I presented you another system of equation, and with the augmented matrix already in the row echelon form or the row reduced form. So then we saw that the equation system of equation is consistent and it has a unique solution. I also found out the solution, and there are three inferences that we drew from all these three problems. So the second category is computing the determinant of the following matrices. So determinants, you might be already aware about how to calculate determinant. So let me calculate the determinant from various properties of the determinants. Like the determinants in general can be calculated in this manner. So let's say, so let us pick the first problem itself. So then the determinant would be like go in this fashion. So pick up the first row, so 2 6 7 9 1, that is one way of calculating determinant. 3, but since it is like the approach is I plus j, that is which element you are picking up and which row and column number it is present in. So this 3 element is actually present in row number 1, column number 2. So I plus j is 3. So there comes an additional negative sign which we'll take care later. Yeah. Then this fourth element is present in first row and the third column. So minus 1 is equal to 1 plus 3, that is 4. 8 9. So this is one way of calculating the determinant. Like there are, you can, without having to go into calculation of determinants in this traditional approach, you can apply several properties of the determinants that you already studied in your previous week, and can make the determinant make the problem of finding out determinant more simpler. So these three problem will be based on that approach, like using the properties to ease out the problem of finding determinants. Yeah. So let me take the first problem. I think it was problem number 4. Yeah. 4a. So the matrix was given as 2 3 4 5 6 7 8 9 1. Yeah. So like the determinant remains unchanged if you perform some elementary row operation again, just as you performed elementary row operation to reduce the matrix to a row reduced form. So if you have such scope of applying some row reduced some elementary row operation that would help you in solving the determinant, then you are free to use that row operation. So in this problem we will always look for like making any particular element to be 0. So if you are able to make a particular element to be 0, then remember we were adding the minor or the like this particular matrix is called the minor. So we were making the minors multiply with a row element. So if you are multiplying, if the element itself turn out to be 0, then you don't have to bother about carrying out the determinant of the sub matrix, like 2 cross 2 matrix. So our main intention would be like if we can reduce the element to 0. So there is scope for that in this particular problem. So what you can do is you can change the second row as follows. So this is an elementary row operation. I'm just adding a multiple of any other row to another row. So I'm multiplying, I'm adding minus 2 of R1 to R2. So this is a valid elementary row operation. So you just can't perform any kind of row operation. So only the allowed row operations are like allowed in this scenario. So given this row operation, so the equation modifies as, so 5 minus 2 into 2, 4, that is 1. So this one becomes 0 and this is minus 1. So here right now you can expand in terms of this element. So in this, along this row you can expand your determinant, and then from this particular element the contribution would no longer be existing. So what you write is minus 1 of, the 1 lies in the second row and the first column, so 2 plus 1, and the element itself is 1, and you multiply with 3491, and then you don't have to bother about 0. So again you have minus 1, and minus 1 lies in like the second row and the third column, second row and third column. Yeah, excluding this particular row and this particular column which contains the element. This is the submatrix 2389. Similarly here I've excluded this particular row and this particular column. That is how I got 3491. So this is the minor which I'm considering, and right now minus 1 of 2 plus 1 is again minus 1, so 3491, and it becomes plus 2389. So now it's an easy calculation. So 3 1s are 3, and this. Yeah. So this is what is I have exploited this particular elementary row operation, and like eased my way out through the process of determinant calculation. So now let us go to the second matrix, which was given by this. Yeah, this is a 4 cross 4 matrix. So right now you will get to know what is the power of the elementary row operation. So let me just write it. So it is a 4 cross 4 matrix. Yeah. So the way to find out the determinant would be, the very first step is to look for element 1, element with which is with value 1, present in which of the column, the very first occurrence of element 1 in which is in which column. So that is in this particular column. So obviously using this this 1 as your pivot element or as your main focus element, you can utilize it to make all other columns to be, all other elements in that particular column to be 0. So that is a easy way to do. So you can modify R1 as twice of R3, since 1 is present in row 3. Yeah, you're doing that and making it 0. R2 can also be done like that. So what you have to do, you have to add twice of R3, so that would make that element to be 0, and then R4 would be transformed as just R4 plus R3. So after you follow this row operations, so obviously you have all other elements except the third row to be 0 in this first column, and with that row operations being performed throughout, the other value changes as follows. Yeah. So you have to perform now the determinant calculation is very easy. Just you have to expand along. Say you're planning to expand along this one element. So you can write it as 1, and obviously the sign you have to take into consideration. So this 1 is present in third row and first column. Yeah. Yeah. Similarly, right now you have a 3 cross 3 determinant. You can either go through the traditional way of calculating it, or you can again perform row operations on it with the intention of making any element to be 0. Like you can make R2 go to as like R2 plus of 3 of R1, that would make, sorry, minus of 3 1, that would make this element, sorry, this would be, yeah, plus 3 of R1 would make this to be equal to 0, so this would go to 0. So again, that you can change R3 to be R3 minus of 3 R1, so that would make this element to be 0. So then you can just expand along this minus 1, and obviously these two submatrix element will change. So after you perform the row operation, you can easily get what is the value of the determinant. What is the value of the determinant you will get. So this is what is the power of the elementary row transformation. So now let me go to the third problem, which is a bit tricky. So that is being taken from the exercise itself, like not from the exercise but from the example present in the lecture. So let us see how to find out the determinant using the properties. It was a C matrix. C is equal to 1, 1, 1, A, B, C, A square, B square, C square. Yeah. Yeah. So right now there is one property of the determinant. So if any of the two rows becomes identical, or any of the two columns become identical, so then the determinant is 0. So that property can be applied here. So we can again perform row operations to actually achieve such a matrix where two row or two columns become 0, two columns become identical. So the row operation that is valid here is, or the column operation that is valid here is C2 goes to C2 plus C3. So when you do that, you have something like this: A plus A square Yeah, so wait, before this actually it is, let me just go about this way. So we are planning to make two columns identical in this. So like this requires some intuition. So how to go about it? So so let me just make C1. Yeah. So in this way I would get 1 plus A plus B, 1 plus C. Yeah. Then I can go as follows: C2 goes to C2 plus C3. Yeah. A plus A square, B plus B square, and C plus C square. A square, B square, C square. So I can take AX column common from all this column. This second column I can take. Yeah. Yeah. Then can pull out ABC from this second. ABC can be pulled down. So this makes the column 1 and column 2 to be identical. So since I already said that if two rows or two columns become identical, I can write it, then the determinant of the matrix given by this particular form turns out to be 0. So that is what the determinant properties are about. And there is another property of the determinant, that if any one row or any one columns happen to have all the elements to be 0, then that determinant is also equal to 0. Similarly, if there are any columns, so in this scenario also the determinant turns out to be 0. So that was about determinant. So yeah. So again we have a linear system of equation whose augmented matrix is of this form. So is it possible for the system to be inconsistent? If not, then explain, or if yes, then also explain. And for what values of beta will the system have infinitely many solutions? So this equation itself, it looks like this matrix form. This looks like written from the homogeneous set of equations. So homogeneous set of equation has the form given as this. So the right hand side is always equal to 0. So this is one such homogeneous equation. So all these terms are 0. So these are the coefficients, and since it's a 3 cross 3, so their unknown variable is 3. There are 3 unknown variables, and this is the matrix of the coefficient. So it is asked that is it possible for the system to be inconsistent? So any set of homogeneous equation has one trivial solution. That is, let's take something bx2 equal to 0, then cx1 plus cx dx2 equal to 0. So if this is a system homogeneous equation, then x1 equal to 0 and x2 also equal to 0 is always a solution for this set of equation. So this particular solution is known as a trivial solution. It's a trivial solution. So since this solution always exists, so that is why it is not possible for this system to be inconsistent, because 0, 0, or for this element, since for this system of equations, since it's a 3 cross 3 matrix, 0, 0, 0 is always a solution of this equation. So it is not possible for the system to be inconsistent. And in the point of view of the, let's say, the rank of the matrix and the also the rank of the augmented matrix and the rank of the coefficient matrix, so you'll get to see that the rank of the augmented matrix is always equal to the rank of the matrix of the coefficient for this scenario, for the case of homogeneous equation. So that says that there is always the equation system of equation is consistent. Now whether it will have infinitely many solution or it will have an unique solution. So for the case of unique solution, this solution is always satisfied, like, so that is a case of one particular solution. So for the case of infinitely many solution, what it is required to satisfy the any of like the second of the three criteria that I mentioned. So that was the rank of the augmented matrix is equal to the rank of the matrix of coefficient, but it is less than the number of variables present. So in this case the number of variable is 3, so it should always be less than 3. So for this particular set of equation, so what we have is, yeah, so let us perform row operations and reduce it to a row reduced form. So and then we can check what is the rank of the matrix. So it is very important to reduce it to a row reduced form. So that thing can be done by performing the row operation like this. So this makes the elements in the first column, apart from the leading row containing the leading entry, to be 0. So the other row also changes. Now on the second row it is R2 R1 will change as R1 twice of R2, and R3 will be thrice of R1. And then it will be that R3 minus R1 minus 2 R1, so that would make minus 1 1 B plus 1 beta plus 1 minus so this is thrice of R2, beta plus 1 minus thrice of R2, that is, yeah, so this all were the augmented matrix. Yeah, so this was the augmented matrix, and like this was the matrix of the coefficient. I reduced it to the row reduced form, and right now the rank, for it to be like have infinitely many solution, the rank of the augmented matrix and also the rank of the matrix always had to be less than the number of variables. So that can be achieved only when beta minus 2 is 0. So if beta minus 2 is 0, then this particular thing goes to 0. So this goes to 0. So that would make the rank of the augmented matrix and the rank of the matrix to be equal to be less than 3. Yeah. So for value of beta being equal to 2, we have this set of homogeneous equation to have infinitely many solution. So that is what it was required, and right now similar exercises can be performed on the next problem. So yeah, so this problem was being done. So in the next problem we have a linear system whose augmented matrix is of this form. So right now this is not a case of homogeneous equation. So for what values of a and b will the system have infinitely many solution, and also it is being asked for what values of a and b will the system be inconsistent. So there are two exercises asked here. Yeah. Yeah, so again the job is to analyze with the help of the inferences that we achieved with the help of knowing the rank of the matrix and the rank of the augmented matrix. So let us bring it down to a row reduced form. Yeah. So with this row operations easily, like these two element will become 0, and we have the other rows as yeah. Now on the second row also we'll perform row operations with the help of the second row. Yeah. So that will make the entries in the column second would be 0 except the 1. So now look into this. This is now a row reduced form. Now it is being asked for which scenario will this system of equation have infinitely many solution. So for infinitely many solution, it is it is important that the rank of the augmented matrix is equal to rank of the matrix. That's fine, but that has to be less than the number of variables. So since this is a 3 cross 3 matrix, so the ranks has to be less than 3. So that says that this row should have 0, all the elements to be 0, because had it contain one non-zero element, then that would make the rank of the matrix to be equal to 3, which is equal to the number of variables. But we want infinitely many solutions. So that, like, to have infinitely many solution, we should have the third row to be equal to 0, that is a minus 5 equal to 0, and also b minus 4 equal to 0. So these are the values of a and b that would help you, that would say that if these are the values of a and b, then the system would have infinitely many solution. Now the next criteria is what are the values of a and b that could make the system inconsistent. So inconsistent criteria was rank of the augmented matrix is unequal to the rank of the coefficient matrix. So, and obviously it is known that the rank of the augmented matrix is always greater than the rank of the matrix. So that says that for this matrix M, if it needs to have a rank lesser than the entire matrix, then it is necessary that this particular element goes to equal to 0. So then we can say that yes, rank of this matrix is not equal to the rank of the original matrix, and it is also required that b minus 4 to have a non-zero value. So that says that a equal to 5, yeah, a equal to 5 would make rank of a equal to 2. So this third row, it becomes 0. So rank of a is equal to 2, and it is for rank of m to be great, like not equal to rank of a, it is required that b minus 4 is never equal to 0. So b is never equal to 4. So to make the system inconsistent, a can take value of 5 and b can take any value, any integer without 4. Except 4, it can take any integer. So there can be several possible values of b. Let's say 5, 1 would make the system inconsistent, 5, 2 would make the system inconsistent. Likewise, except this element being equal to 4, that would make the like for that values of a and b, we would have an inconsistent equation. Yeah. So all these problems, it drives home the all three inferences that we actually started with. So this is one of the inferences for the system to be inconsistent, and this is for the system to be consistent and have infinite solution, and for the system to be consistent and unique solution. So right now let us go to another category of problem, which is we have to find we have to consider there is a mapping of vectors. So this is can be considered as an operator which is operating on a vector space like represented by x. So elements of the vector space are represented by x. Yeah, so element of the vector space V are represented by x, which has two elements x1, x2. So, and there is an operation on the vector space V that is given as follows. So the operator acts on an element belonging to a vector space, x belongs to V, and the operation goes as follows. Yeah, this is how the operation is. Basically, if you were to think in terms of the vector, two-dimensional vector that we usually study in physics, x and y. So this function is basically an operation that is giving me the norm of the vector, that is the length of the vector, x1 square plus x2 square root of that. So it is being asked that whether is m, this operation is a linear operation or not. So from the definition of linear operation, this is, suppose m is an operation which is being performed on a vector x, and if I were to multiply the vector by the constant, let's say alpha, then if the same operation has been carried out, then the results would just modify as follows. So this is the criteria for an operation to be linear. So let us see whether this criteria is being satisfied or not. This is the criteria for operator M to be linear. So we had M given as so let us first start with the left hand side. Let us multiply alpha to x. Alpha to x multiplication is that alpha x vector is alpha x1 x2. So alpha of x1, alpha of x2. So that would make the operation to be alpha x1 whole square, alpha x2 whole square. Yeah. So this is how the equation changed. Like this is my uh, form for this particular value for this particular operation. So what happens actually? So for alpha here, for alpha less than 0, the equation changes as with a minus sign because there is modulus involved in it. For alpha less than 0, it has an additional minus sign, minus of alpha. For alpha greater than 0, yeah. So what you see is that, so what you see is that for for all alpha we don't have this, like we don't have this satisfied. We don't have m alpha x equal to alpha m x to be satisfied. So as alpha goes to negative, then this gets violated and we only have this to be satisfied. So that's like says that the operation given by this is not a linear operation. But if you restrict your alpha to be only positive for alpha greater than 0, if you restrict your like the scalar field, so alpha is essentially a scalar field. So if you say the vector space like has a scalar field given by only positive real value, so in that scenario your operation M is linear. But if you have a vector field which like acts on a scalar field which has both positive and negative real values, so in that case you can't say that is a linear operator. So this is what is meant by linear operators. Yeah. Now let us come to the topic which is linear dependency again. So we have n vectors in the real space. So that has been represented as follows. So x vector has n components, and we have to prove vectors, these vectors, if the vectors if they are linearly dependent, then x the x vector is singular. So that is something we have to prove, that is the determinant of the x vector is equal to 0. So let's go about solving that. Yeah. So we already know from the previous class then the linear dependency or linear independency can be is satisfied when the following conditions is satisfied. So for the set of vectors we write so since they are already said like if the vectors are linearly independent, so this is the equations that we write, and it can be rewritten in a matrix form. So how to write in a matrix form? That would be so in this case it would be 1 cross n, and C would be n cross 1. So 1 cross n would be our vector, and the coefficients are as follows. Coefficient matrix, it's n cross 1 matrix, so there are C1 till Cn. So I've recasted this equation in the matrix form with x and c value given as like this, and then since this is a homogeneous equation, so the trivial solution will be always 0. So with 0 comma like x1 x2 xn, like they are 0, like sorry, the c1 till cn equal to 0 is already a solution of this. Now let's see if there is any non-trivial solution or not. So non-trivial solution would only exist if my determinant of this x is equal to 0. So that is because so remember the case of infinite solution for the case of homogeneous equation. So homogeneous equations were allowed to have infinite solution only when determinant of the augmented matrix is equal to determinant of the coefficient matrix, and it had to be less than the number of variables. Yeah. So sorry, the rank of the augmented matrix and the rank of the matrix coefficient had to be less than n, that is the number of variable. So in my case, this is my each vector. So each of these vector is like they all are vectors, so they all have their individual components present. Yeah. So if I were to write it in like complete matrix form, so if each vector has n element, that is n cross n matrix. So the rank of the matrix should be less than this n, should be less than the number of variable present, and the determinant from the method of determinant we can actually get the rank of the matrix. So that is obtained as follows. So the order of the non-zero submatrix, order of largest non-zero submatrix with determinant as non-zero, is the rank of the matrix. So that is another way of calculating the rank of the matrix. So suppose you have n cross n matrix, and then the determinant of that matrix, the determinant of that n cross n matrix turns out to be 0. So then that would say that rank of the matrix is not n. You have to look for another submatrix within that matrix that would yield a non-zero determinant. So if this was not equal to 0, let's say if this was equal to equal to 5, then we would have easily concluded that rank of this matrix is also equal to 5. Rank of this matrix is also equal to n. So but if this is equal to 0, then we have to look for the submatrix which has rank, which has submatrix which has determinant equal to non-zero. So for that, obviously the submatrix will have a dimension which is lesser than this dimension n cross n. So it can be n minus n, this can also be the case, or the next step we can go is even decrease the size of the submatrix, and likewise we will find the largest submatrix with non-zero determinant. So that actually brings down to the conclusion of this particular problem, that if we want rank of the augmented matrix to be lesser than the number of variables, then we need to have this particular n cross n matrix to have a zero determinant as 0. So then only we would go to a submatrix of size lesser than the n cross n matrix, say n minus 1, n minus 2. So with that we can conclude that the rank of the matrix can be n minus 1 or n minus 2 depending upon the size of the submatrix. So that actually leads us to the conclusion that on solving this particular system of linear equation can have a non-trivial solution if the rank of this matrix is lesser than the number of variables n, or the determinant of this matrix is equal to 0. So in words, if I am to write, then we have that non-trivial solution is allowed when the determinant of the matrix is equal to 0 or A is singular. So when I say non-trivial solution is allowed, that means that C1, C2, Cn can have values which are not 0. Yeah. So that actually says that the vectors x1, x2, xn, they are not linearly independent, but they are dependent. Because since C1, C, all of them, if they were necessarily 0, then it would have been case of linearly independent scenario. But since it has been like there can be a scenario where if the determinant turns out to be 0, then in that scenario we will have the x1, x2, xn vectors to be linearly dependent with each other. So that actually proves the next problem. Yeah. Now we have to show that this particular sets of vector forms a basis for the 3x3 real dimension. So basis is something that you might have learned, that like the all others, like if for a three-dimensional plane, if we choose a basis, then all other vectors in that plane can be represented as a linear combination of that basis. So how to prove whether those three elements it forms a basis or not? Does it forms a basis of like R cube or not? So in this again actually let us write. So this is nothing but like for this other scenario. So we had x1, x2, n vectors out here. So right now we have 3 vectors, because this is a case of 3x3 real 3x3 dimension. So we have 3 vectors. So the matrix corresponding to this particular problem 3x3 would be given by each element, like -2, 1, 0. So here this is x1 vector, x2 vector, this one is x3 vector. Yeah. So we know the basis vectors, they are linearly independent with respect to each other. Basis vectors main criteria is they are linearly independent with respect to each other. So if I were to check whether this particular set, does it forms a linearly independent set of vectors, if they form linearly independent set of vectors, then it would say that it forms a basis. So let me check whether it forms a linearly independent set of vectors. So from the previous problem, it is very clear that if the determinant of the matrix turns out to be 0, then it does not forms a linearly independent set of vector, then it is a linearly dependent scenario. So let me find out the determinant of this matrix. So I will expand along this because there is a 0 present. So when I do it, this will be so with this we have 2130 1 minus 2 2 1. So again it will be minus 3 plus that is 2. So in this case we have the determinant to be not equal to 0. So had determinant being equal to 0, then we would have no non-trivial solution were allowed. But now since determinant is equal to 0, we don't have non-trivial solution. We don't have non-trivial solution. To which equation? To this equation. Yeah. To this particular equation, we don't have a non-trivial solution. So we only have the trivial solution, that is this. So if this were to be satisfied, then since the determinant is not equal to 0, we should have C1, C2 and C3 equal to 0. So that actually says they are linearly independent. x1, x2, x3. Yeah. So they are linearly independent. Yeah. So we have proved the given set of vectors. So this set of vectors, it forms a linear independent set of vectors, or it forms a basis in our 3 cross 3 R real dimension. Now is a problem like we have to, in the last class we have seen how to prove whether a 2 cross 2 like whether a subset or a set forms a vector space or not. It had to obey certain criteria. Right now we will prove whether a given subset forms a subspace or not. From like we have the original set which forms a vector space, like 2 cross 2 matrix, it forms a vector space. Right now we have to check whether the set of 2 cross 2 diagonal matrix, so 2 cross 2 diagonal matrix is a subset of 2 cross 2 matrix. So we have to prove whether this W, it forms a subspace or not. So let us go about solving this problem. So the way this problem is solved is similar to how you solve problems to find out whether a given set is vector space or not. So yeah, so obviously this set, which is represented as follows. Yeah, this set, first of all, it's a non-empty set. It's non-empty, obviously, and also it's a subset. It's definitely a subset of 2 cross 2 matrix set. And let us now check other properties. So the other properties is that the first property is the closure under vector addition. That was our very first property. So let us speak of two matrix from this set. So A and B both are 2 cross 2 diagonal matrices. So in other words, we can write them as this, and B also assumes the same form. Then what we see is that A plus B is right now given by A1 plus B1, A2 plus B2. Yeah, which is clearly a diagonal matrix. So obviously A plus B also belongs to the subset W. So what we have achieved is that we have taken two matrix from this subset, and we have shown that under vector addition the resultant matrix also belongs to the same subset. So it's closed under vector addition. Now the second property was, is it closed under scalar multiplication? So let's take a scalar from the real field, so and also a matrix from the subset. So since A belongs to W, so A has the same form, it has a diagonal form. So let's see whether C cross A belongs to W or not. So C cross A, just like similar matrix multiplication, we would have CA1 0 CA2. Yeah, this belongs to, it does belongs to W because still it's a 2 cross 2 diagonal matrix. Yeah, so hence it's closed under scalar multiplication. Similarly, you can check whether it has an additive identity. So the check for additive identity would be similar, like it has to, the additive identity for this case, let's take this particular matrix A itself. So this belongs to W. So the additive identity would be the null matrix itself. So this is also a diagonal matrix with like this principal diagonal values A1 or A2 in this scenario at 0. So we have A plus O is equal to O plus A. In any way you perform the addition, and it turns out to be A itself. So here O is the additive identity, and it belongs to W set. So similarly there exists inverse also. So existence of inverse. So for any A, let's say for belonging to W, that is A has the form, we can negate its components, that is form another matrix as follows. So that is again a diagonal matrix. Now if you perform a vector addition of both of them, we expect to get back the identity element O itself. So for you pick up for any A, there exists a dash, which is just the components are negative of the original matrix, and that also belongs to W. So there exists an inverse. Yeah. So that proves all of the three properties. One is the existence of inverse, all of the four properties: existence of inverse, additive, existence of identity, closed under vector addition, and also closed under scalar multiplication. So given all of these properties is being satisfied by the subset W, so W satisfies all of these properties. Yeah, W satisfies all of these properties. So that says, so W is a vector space. Yeah, it's a vector space, and since W is a subset, it's a subset of 2 cross 2 matrix. So W is a subspace 2. Yeah. So that is how you prove whether it's a subspace or not. First of all, you have to prove whether it's a subset of the original set, and after it has been established, you check all the four laws of the vector subspace, and if it satisfies all four, then you conclude that it is a subspace of the original vector space. Yeah. Now the next problem is, suppose if you have a vectors which are linearly independent, suppose u, v, w are linearly independent, and you have to show that these vectors which are given by u plus v, u minus v, and u minus 2v plus w, they are also linearly independent. So that is what something you have to prove. Yeah. So since you already have u, v and w to be linearly independent, suppose you start with this equation, the equation for linear independence. So you have to prove whether u plus v and u minus v u minus 2v plus w are these three vectors linearly independent or not, provided u, v and w are linearly independent. Yeah. So since u, v and w's are linearly independent, then that would say that c1u plus c2v plus c3w equal to 0 would mean that c1, c2, c3 is equal to 0. So if u, v and w are given linearly independent, so this condition is satisfied by u, v and w. Now let's manipulate this particular equation. So if from this particular equation, so if I get to prove that x, y and z, they are equal to 0 indeed, so if I'm able to prove that, then I can say that this u plus v, u minus 2v plus w, then they are linearly independent. So let us find out the value of x, y and z. So let us separate out u, v and w. So when I separate out u, v and w, so u from there is x plus y plus z into u. So I have separated out u. Similarly, I can separate out v. Yeah, so I have separated out v, and w is only there in last term. Yeah. So this is my like the equations with u, v and in terms of u, v and w. Now since u, v and w are they are linearly independent, then their individual coefficient from this very rule, the individual coefficients are 0, that is Yeah. So this is something which is satisfied by x, y, and z. So from third equation we have z equal to 0. Just name it as 1, 2, and 3. So from third equation we have z equal to 0. Now let's put z in 1 and 2. From 1 and 2 we have x plus y equal to 0 and x minus y equal to 0. So definitely all of this says that x and y both equal to 0. So from here we have, from above, x equal to y equal to z equal to 0. So we have been able to prove that. So we started with this, and using the very fact that u, v and w, they are linearly independent, using that fact I have achieved that x, y and z turns out to be 0. So that says the vectors u minus v, u plus v and u minus 2v plus w, u minus 2v plus w are indeed linearly independent. Provided, this is very important, provided u, v and w are linearly independent. Yeah, this is about the linear independence thing. Now let us move to the next problem. Yeah. So we have a set of matrices. So these are Pauli spin matrices. So this you will come across in quantum mechanics. So these matrices are very important, and it has been used in the study of electron spin. So when you solve the hydrogen atom problem, you will hydrogen atom problem and associate spin to the electron. So that time you will come across this kind of matrices. They are known as Pauli spin matrices. Now obviously we have like the imaginary, so you can see there is an I appearing in this equation, in this matrix element. So it's their matrix of order 2 cross 2. Definitely they are 2 cross 2, all of them are 2 cross 2 matrix, and they are in the complex plane. So that is why the plane, you can say the vector space is 2 cross 2 complex matrix space. So you have to show that this set is linearly dependent in C22, like in this vector space it is linearly independent. Now let us go about proving this. So let us check whether they are linearly independent or dependent. So to check linearly independence or dependence, we obviously start with the very equation we just started with, that is C1 of the first vector of the first matrix in this case, plus a coefficient into the another matrix equal to 0. So in this case it's a 2 cross 2 null matrix. So this matrix equation gives me C1, like I would write this equation in this fashion, like there is 0 of C1, C1 0 plus minus IC2, IC2 0 plus C3 0 0 minus C3 equal to, when I add them it is C3, and then I have from the first I have this, and then C1 minus IC2 is from the second terms, and then C1 plus IC2 and minus C3. So if they are linearly independent, then I should have C1, C2, C3 all to be 0. And if they are not linearly independent, then at least one of them has to be non-zero. So let's see what is the value of C1, what is the value of C2, and what is the value of C3. So from the equality of matrices, we have C3 from this two element. We have C3 equal to 0, that is for sure. And then the other is this is for the other scenarios. So from this case, again what we have is minus of C1. So both of these, it so all of this C1, C2, C3, they are linearly independent. Like they turn out to be 0. That is why these vectors, these Pauli spin matrices, they are linearly independent. Yeah. So okay, so this problem is done. So there it turns out to be linearly independent. So yeah, like this, there's a typo involved. So we have to check whether S was linearly independent or dependent. So it turns out to be linearly independent. Yeah, so having solved all of these problems, so today mainly we focused upon the notion of the rank. How can the rank of the matrix can help us say the inconsistency or consistency in the set of equations. So that is what we came across in the first few problems, and the next then we move to something called linear operation, whether a subset is linear, whether an operation is a linear operation or a non-linear operation. That is what we solved in problem 7. And in problem 8 we saw that if the vectors are linearly independent, then the vectors written in the matrix form, the determinant of that matrix turn out to be singular. So this is what we saw. So let's say x1 has 3 components, 3 0 1, x2 has 4 5 0, and let's say x3 turns out to be is 6 0 7. So this matrix, like with the vectors written as a form of columns, so if this matrix determinant is singular, is equal to 0, then the vectors, these individual vectors, are linearly dependent. So that is something we can do from just by looking at the determinant. And the other way around is to write the vectors in this form and solve the simultaneous linear equation as we did for the Pauli spin cases, and find out whether C1, C2, C3 are all equal to 0. If they are all equal to 0, then it is linearly independent. If one of them turns out to be non-zero, then it is linearly dependent. So either you can conclude it by calculating the determinant, or you can check from the coefficient values. Yeah, so this was for the case of proving whether it's a basis or not. So to prove whether a set of vectors form the basis of that particular vector space, we have to calculate, we have to find out whether the set of vectors is linearly independent or is it linearly dependent. If it is linearly independent, then that particular set of vector represents a basis. And there is something called as dimension. So dimension is the number of elements in this set, in the basis set. So here there are 3 elements, that those are linearly independent, and so the dimension of this vector space is 3. And so similarly, if there is R2 cross 2 matrix subspace or R2 plane, so in that case the basis space would have two elements which are linearly independent. So the dimension is the number of vectors present in the basis set. So that is something was about the dimension. So then we came to the problem where we have to prove that whether a subset forms a subspace or not. So we had a parent vector space. So this is the parent vector space. This is a parent vector space. So it's a 2 cross 2 matrix. So then W is a subset of this parent set, and we have to prove that whether this W it forms a subspace or not. So we again have to prove all the criteria of the vector subspace, and then we concluded that if it matches all the criteria, then it's a subspace of the parent vector space. Then again, the case of linearly independent scenario, we have to prove whether whether the determinant, if it's a linearly independent case, then the determinant had to be like non-singular, it has to be non-zero, or other way is to prove each coefficients turn out to be zero. And that was being done in the Pauli spin matrix. So that is all for today's class. So yeah, if you have any doubt regarding any problems, you can ask me right now. So this was the conclusion from the first, how to determine what is the fate of a system of equation, whether it is inconsistent, consistent, or it has unique solution or infinite solution. We can know from the rank of the coefficient matrix and from the rank of the augmented matrix, and from the rank of the matrix rank of the matrix can also be known from the determinant. So order of the largest square submatrix with non-zero determinant would give us the rank of the matrix. So suppose if you have a n cross n matrix and the determinant of this matrix is 0, so you find another submatrix within this. Submatrix within this means, like, let's say you pick up n minus 1 into n minus 1 submatrix. If that turns out to have non-zero determinant, so n minus 1 would be your rank of the total matrix. So if that also turns out to be 0, so let's say if this also turns out to be 0, so go find out another smaller submatrix, n minus 2 into n minus 2 matrix, and keep carrying out this procedure till you find a larger square submatrix with non-zero determinant. That order of that matrix would be the rank of the total matrix. So that is something called as rank of matrix, finding out rank of matrix using determinant. Then there are homogeneous equation, as I discussed, like the right hand side are all zeros. So it can either have trivial solution or it can have infinite solution depending upon the rank of the augmented matrix and the rank of the coefficient matrix. Then there is the basis and dimension, and then proving whether a subset forms a vector subspace. So that is all about today's class. So if you have any doubt, you can ask me right now. I have approximately 5 minutes, so you can ask me right now if you have any doubt. So in case there is no doubt, let's end today's class and let's meet in the next Sunday again from 4 to 6 p.m. And in that I'll discuss the problem based upon the upcoming week's lecture. So yeah, let's wind up this session. Thank you everyone.